then none of the sequence, none of the terms of this set will belong here. Is that clear? You see, this is why I draw pictures. It's now evident. I don't need to write anything more. Clear. No element point of set A belongs to. I just give you one comma 3/2 open. If it were a limit point, it should have contained at least one more from that set, but none of the others are here. So it's not possible. It's not a limit point. So this brings out the difference between R and R. Same type of question, but more familiar space. So consider the set A. This is a nice set actually. M plus root 2 times n, mn natural numbers as a subset of R. Okay? Question: find the limit points of this set. If you just add only m, no root 10 and so on, just this, then this is just integers and we can plot the points. Integers will have no limit. It's a discrete set, no limit points. But I just put one more, m plus root 2 times n. Okay? Now what happens? So this is usually written as z. Well, first write plus root 2 times z containing R. So this is equal to an abelian group. It's an abelian group. It's containing here. Okay? But no mind at the moment the group structure, they will have occasion to exploit that this is a group. But at the moment, what do you guess? Is there any guess? Does it have any limit point at all? I am just taking only integers plus some integer times root 2. So now it becomes a little complicated. So ask yourself a simpler question. I give you a specific number. What about 0? Is 0 a limit point? Can you find the sequence of elements from this set? So I draw picture here. This is origin 1, 2, 3, minus 1, minus 2, minus 3, and so on. Okay? Now then I should draw root 2, and then 2 root 2. Okay? 2 root 2 will be close to here, and so on. And then 1 plus 2 root 2, and then 2 root 2 minus 1. I form all kinds of integer combination. Now what happens? What is the limit point set? This original limit point. Okay? Things become a little complicated. It turns out A is things. You know, this is a bit of a surprise. Why is it's something very familiar to us. Root 2 is familiar to us. Okay? This is a very familiar set. Subspace of a very familiar topological space, most basic. And yet it is surprising that this is things in R. I will give you idea of proof. Okay? The first thing is to show that origin is a limit point. Okay? So we will first show that origin is a limit point, and then from then on we will be able to see that every point must be a limit point. Use some trick with this special case, but I will not use any trick, I will not do any such thing, but just directly show. I give you the idea of that origin is a limit point here. So suppose origin is not a limit point, what does it mean? That means that there is some neighborhood which contains only origin from that set. There is no other element in this neighborhood. Okay? That means, so suppose 0 is not in a bar, then there is the smallest element in here. Well, let lambda, okay, that itself is, okay, let lambda be, okay, so you really have to argue that there is a smallest element, okay, in here, lambda in, actually that is, you see this small lambda b, lambda possibly b, the smallest element in A closure. Okay, A closure will have to contain some positive elements, also some negative elements, because the group which contains some positive and negative numbers, so it will have to contain some positive smallest element. Alright, now what you do is you have to show in fact, this is not difficult to show, in fact lambda itself belongs to A. If lambda is not in A, then lambda will have to be a limit point, meaning there will be a sequence of points lambda n belonging to A converging to this, but if that happens, then I take differences, the differences will converge to 0, but 0 is not a limit point, so it has to be the case that lambda itself belongs to A. So otherwise lambda equal to limit of lambda n going to infinity, lambda n I write belongs to A, but then consider lambda n minus lambda m, or lambda n minus lambda n plus 1, just why take it complicated. Look at this set, these elements, because A is a group, this will belong to A and this will go to 0, and we have shown that this is a sequence of points which is going to 0, so that means 0 will be a limit point contrary to the hypothesis. So lambda belongs to A. Moment lambda belongs to A, then all multiples of lambda will be in A, alright, because A is a group. But the claim is the group A, see this set A is a cyclic group generated by lambda. Claim, that's the next claim. It's a nice beautiful problem. Claim A is equal to z times lambda. Okay? See, this has to happen, because if this is not the case, then I tell you why it has to happen. So actually A belongs to, claim is A belongs to this, and also root 2 belongs to, sorry, go from some A belongs to string for some name. This will do for us, and then n also belongs to lambda for some n. Okay, these two should happen. See, once you have a group structure, you can exploit that. This is a closest element that we found out. Now I can take 2 lambda, 3 lambda, 4 lambda. These are all in A. Because lambda is in A is a group, that will mean that all multiples are there. So minus lambda, minus 2 lambda, all these are there. Okay, these will all be in A. Now, if A is not one of them, so I just look at some integer. Okay, see, I claim that integer is a subset of this. If it is not a subset of this, some integer is a little bit away. So here I have some m, and then m plus 1, somewhere this type of thing should happen. But then I can look at the difference. Either this difference, some integer is caught here like this, then either this difference is less than lambda or this difference is less than lambda. That cannot happen because lambda is the smallest positive number and I can take subtraction. Okay, So that is not possible. Some integer must have to belong. Same way n to 2 will have to belong. Otherwise, say for example some root 2, some multiple of root 2 and root 2 is caught between two successive things. Okay, two successive multiples of lambda. Then I can just subtract this. This will be something which has length strictly less than lambda and positive, and that will belong to A. That's not possible. Or this will be less than lambda. That's not possible. So you see that this, in fact, for all. Okay, in fact, this is true for all. And that will mean that A is in fact this. So after you make these observations, now you write what this means. M is equal to, okay, so in particular I can write 1 is equal to K times lambda and root 2 is equal to some L times lambda, K and L integers. But then you divide by the one by the other. You simplify that root 2 is lambda will get cancelled and by K. This is a rational number. Okay. Not possible. So you use the fact that root 2 is irrational, and that proves that is not possible. So here is a situation where a set which looks like discrete, just only integers, but it is dense in the set of real numbers. Okay. Sometimes can be a little bit involved in the sense you may have to go a little bit outside the domain. There is nothing special about root 2. You could have what? If you had used m and instead of root 2, you use some irrational number. If the other one integers, it would still work. Same proof. Okay. Another thing, this is in fact a very standard question. The previous question is standard, but the next question is even more standard. Find limit points of the set. So I call it A again. Sin n in integers. Okay. So sin n means sin not n degrees but n radians. Okay. When we simply write sin n, that means sin n radians. Just for emphasis. Now, how do we do this? What is the guess? So it looks like I am just taking on the real line some integers, and for each integer I am computing the value, the sign of that number, and making a set out of it. So whatever it is contained in the range for the sine function. The range for the sine function is -1 to +1. Very good. So -1 to +1. Whatever the set is, the set of limit point, it has to be contained here. What is it? What is your guess? Any guess? Doesn't matter if you go wrong. Sometimes we all make mistakes. Doesn't matter. Huh? Any guess? Only positive numbers, or only -1, or what? 0? Answer is -1 to 1. Why? Okay. Now, see the way to view this problem is the following. Sine is a periodic function, correct? So if I replace sin n, sin x is equal to sin of x plus 2k pi or 2m pi, right, 2m pi. Okay, sin of x plus 2m pi for any place of x you write n. Now this looks like the previous problem. N plus 2m pi, n varies in integers, m also varies in integers. Of course this is a dummy, it makes no difference to our answer. But nevertheless it's good to keep it. Because now pi is irrational. Now n plus 2m pi, well 2 pi is irrational means 2 pi is irrational. N and m I just vary freely over the integers. So we said C is equal to z plus z2 pi. This is dense. We just saw that. I used root 2, but then the proof was something that used only the fact that root 2 is rational. Same proof will tell me this is dense in all. Dense. But now I have a continuous function. Okay, I have a continuous function and I am just looking at a range of a dense set in the domain. What will be its nature when you look at the image? The image will have to be dense in the image when I restrict the domain. You understand what I am saying? So I write that here. Since C is dense in all, f of C is dense in f of R for any continuous function f from R to R in the place of a real sign. Therefore sign of C, well this means this set of value is dense in minus 1. And this means that limit points of psi n is dense in, well, is equal minus 1. Okay. Is that clear? You can have variation of this thing. Instead of n, I could have written n to 2. Still the same proof would work. Instead of here z, I have z root 2. That's a big difference. Z root 2 plus, so z root 2 plus z times 2 pi. How do I compare? How do I know what is the answer? So that depends only on, so ZA plus ZB. This will be dense if A by B is irrational or B by A is irrational. Just use that and do that. Okay. So, alright. So these are some interesting type of problems which sometimes are asked in various exams. I have written down some more questions. Okay. So, question. So, suppose that A and B are subsets of some topological space X. So, is it true that I take A intersection B and then take closure? Is it the same as A closure intersection B closure? What about if you had, so A union B closure was also. One of them has to be 12. So let us take the first one. What do you guess? Yes? True or not true? Not true. Very good. It's not true. What's a good counter example? Counter example? Sorry, I didn't understand. Oh, if you take one of them here to be empty, then this will be empty. It's also empty. So one nice thing to see, forget all this. What is a good example of a dense set in a topological space that we are all familiar with? We are all familiar with one example of a dense set in a certain familiar space. What is it? This we keep telling our students repeatedly. Somebody can tell me? Rationals, right? We keep on telling rationals is dense in reals. No? So take rationals. Let us take A to be rationals. B to be irrational. Very good. Take B to be irrational. Irrationals are dense. Rationals are dense. So if I take A to be rational, B to be irrational, what is A closure? A closure is over of real line. B closure is over of real line. Intersection is over of real line. But look at A intersection B first. That's empty. And if I take empty set and I take closure, I get empty set. What about the second thing? True or not true? Probably not true, because the first one was not true. But it's true. See, I just prove it one way and I will not prove the other way. Okay? So which way do you want me to prove? I am going to prove one of them is contained in the other. Which way you want me to prove? You tell me. Shall we prove this is contained in here? Okay. So to show union is contained in this, I show each one of them is contained in here. Okay, let us take A closure. So I want to show A closure is contained in this. But first observe that A is zero closure. A is contained in A union B. But this is contained in A union B closure. This is a closed set. So A is contained in a closed set. Implies A closure is contained in A union B closure. Yeah. Same way, so B closure is contained in here. So similarly, B closure is contained in A union B closure. But these two together imply A closure, union B closure is contained in A union B closure. The other way around is exercise part. We're not going to discuss. I have written down a few more things. Alright, now so let us do this following thing. Suppose f from R to R is a map, set map is a function such that f of a plus b is equal to f of a plus f of b on a. Is f continuous? let us examine what are the consequences of such a thing. Okay. So I know f of a plus b is equal to f of a plus f of b for all a comma b. So if you write for example 2a, this is f of a plus a, which is f of a plus f of a plus a plus 2 f of a, and you can do this process, then let's observe that f of ma is equal to m times f of a, and well, if you call ma as b, what do you get? Is you can also show a by m, which is equal to 1 by n times f of a, or f of p by q times a is equal to p by q times f of a for all factors. You can also allow negative numbers, so it doesn't really matter. So if only you can show that f of lambda a is equal to lambda times f of a, then it becomes a vector space homomorphism over the reals. And you know that any odd linear map from real numbers to real numbers is continuous. It is given by f of x is equal to lambda times x, or x to lambda, and it would be continuous. Now the question is, all I know is only this much I can definitely go. But beyond this, can I just say f of lambda times a is equal to lambda times f of a for all real numbers lambda? That I really definitely cannot say. And to say that it is not possible to say is not enough. We have to come up with some example of a function which satisfies this property but is not all linear. And what we are asking is, well, is there a, you see, Q is also a field, right? Rational numbers is a subfield of real numbers. Okay? So I can regard real numbers as a vector space over rational numbers. When I do that, I am asking whether Q linear maps are necessarily or linear. Not at all. They don't have to be. What is the dimension of the vector space all over Q? What is the ordinarity of real numbers? Is uncountable. Okay, C. What about rational? It is countable. If I take q power n for any integer n, it will be again countable because product of countable sets is countable. Okay. If I take direct sum of q infinitely many, countably many copies, even so it will remain countable. The thing is, conclusion is, all as a vector space over real rational numbers is of infinite dimension, beyond in fact dimension, the countability, cardinality of the natural numbers. It goes even beyond. But all we need is, therefore, some vector space homomorphism over the rational but not over the real. Now you have a clue as to how to construct it. Alright? So I will say the following. So what you do is the following. You just choose a basis for reals over rationals. So this time I mean really vector space basis. Let B be a basis, Q basis for real numbers. All I need is the fact that B contains more than one element. Okay, so I could have just, for example, taken 1 and 2, and then maybe dot 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 1. Really, exactly what the thing is not very relevant for us. Then what you do is, so I am going to define a set map. So P from B to real numbers, you just choose anything you like. I will choose it in a particular way. Say P of one of them, I single out one particular one. I just set it to 1. So I write b equal to b naught and 0 b naught equal to b. For all the other things, okay, b belongs to b. Just choose one particular b naught, or that b naught define it b1, all other things is same. Now I have defined a set map on a basis, so it extends uniquely to your vector space homomorphism, because once you know any set map on a basis element, that is a unique way you can extend it to a vector space homomorphism. He extends to a basis and to a homomorphism of vector spaces. So R to R, they call that S. Now this F is non-zero, but it cannot be real vector space homomorphism, because for one to not the same non-zero element it is something, and then the other one it is 0. It cannot be linear or linear. I don't know if you understood what I said, so I write it just a little more in detail. So F is not or linear. Okay. This means because choose a b not b naught in b. Okay, this is in b. Choose an element. F of b is equal to 0. So if it is or linear, I could have written it like e by b naught times b naught. So this would have been equal to what? This would have been e by b naught times f of b naught is 1 e by b naught. You see that? If it were or linear, if yes, were or linear. So we have got picture. Okay. Now we can very easily show that this is what did we want to show? We wanted to give an example of a function to satisfy this property. Okay, but not continuous. So I am saying that this will be an example of a function which will satisfy that property. Yeah, because any vector space homomorphism is automatically a group homomorphism, and this is what I have done. So it satisfies this property, but I want to say it is not continuous. To show it is not continuous, I will give you a sequence of points converging to origin, two different sequences. So just take yeah. So you take B. So let A and B a sequence of factor numbers such that A n converges to 1. Such that maybe right here A converges to B naught, B by B. Something like that. Okay? Then I write, so f of An times B naught. This is equal to what? This will be An times f of B naught, which is this. Okay, and this will go to B by B naught as n goes to infinity. But to take the limit inside, f of limit of this n going to infinity A and B naught, this is equal to of B. Here, let B, say B naught equal to B naught, B naught. So you see, you get two distinct answers. So, not possible. Cannot be continuous. Okay? So, there are very many functions which satisfy this property. I will erase that. It is just to illustrate this. Although I have not spoken about connectedness, compactness and so on, I now want to discuss some problems concerning connectedness and compactness and so on. Okay? Let us start off that. If you have any questions about that, this is the right time to ask before I proceed further. Do you have any questions or doubts in this? Okay? At least some ideas are there. The trick is to find a Q linear map which is not all linear. And there are